up the idea of nutrient dynamics. So we've sort of talked about nutrients as toxins, we've talked about them cycling, but we've not talked about how it actually works as far as taking them up and stimulating growth and relating that then to the food web, which after this in the next chapter will lead us to nutrient pollution problems and understanding them. So we'll talk about use of nutrients, about the concept of limitation by nutrients, about resources, ratios, and stoichiometry of primary producers. It's an important topic. And then we'll talk about stoichiometry of the things that eat them and how that feeds back to the community. So we're starting to get into sort of community ecosystem type stuff from the straight nutrient chemical stuff. So when we think about nutrients uptake, we can think about it in several ways. One is that we can think about what the concentration is outside of the cell, and that's S here, and what the uptake rate is into the cell. And it turns out that the enzymatic relationship that explains this goes by this equation. It's called the Michaelis-Menten equation. And what it will do is it will saturate out at high concentrations. Because what will happen is this S over Ks plus S will become 1 as the nutrient concentration increases, right? So if this becomes 1, then V becomes very close to Vmax. So that's the first way to think about it. But uptake is not growth. There's such a thing as luxury consumption. And it makes perfect evolutionary sense that organisms are able to do that need nutrients. Let's say you need phosphate and you come upon a cloud of zooplankton poo or something, and there's all this phosphate out in the environment. If you can take it up and pack it away and save it for a later day, you can grow better, right? So the growth rate does not match the potential uptake rate. It's just the ability, it's why, winter's coming and don't eat more donuts, put on some fat for a later day. Same thing. So growth rate can also be related to nutrient concentrations over the long term. These rates are going to be lower than the uptake rate. And finally, if you look at and that's the Monod equation. And then if we look at the Druff equation, that's the third equation, that actually links the concentration in the cell to above some critical level, the cell can grow, and to growth. So essentially, you can think of this equation linking the first two equations together. Because you got to get it in from outside of the environment, then you got to get the concentration in your cell up high enough that you can actually make your metabolism run. So these graphs are right here. In general, I don't necessarily require students to spit back the equations verbatim, but if you understand the equations, you're going to be able to understand a lot of the arguments that we go throughout this chapter. So I think it's important. It's simple algebra. You've had this level of math since high school, so it's not undoable for you. But this is a graphical representation of these. First, the Michaelis-Menten equation here. And we see this Ks value that I put up there. That's called the half saturation constant. And that is the concentration at which uptake rate, V, is 1/2 of Vmax, right? And so that determines a curve where you get very rapid uptake at low concentrations, and then you eventually saturate out. You just can't take up any more nutrient any faster. So you can imagine then, thinking about this type of equation, if you had an organism that was really limited by nutrient, would they have a low Ks or a high Ks? If they're in a real low nutrient environment, do you want to have a lower Ks or a high Ks?
High Ks.
Why high Ks?
Because you'd want to uptake as much of it as possible.
Well, but the concentration's always low, right? So if you have a high Ks, then that pushes this curve out that way. Even though it gets to the same Vmax, it gets there slower.
Oh, okay.
Right, so you want to have a low Ks. It's like alpha, right? You want a steep alpha for photoinhibition, for low light species. You want a steep initial part of the curve, so the shorter this value, the lower this value is, the higher your uptake's gonna be. But it does turn out there's a trade-off, because if you have a high KS, that means your Vmax can't be so high. We'll get into the ecological implications of that in a second. And similarly, there's a saturation of the Droop equation, where the growth is a function of the concentration in the cell, and this Q0 is some concentration below which, if the cell can't maintain nutrient input into the cell at high enough rates, growth stops completely. And finally, the formulation of the Monod equation is exactly the same, and you know what, these are switched here. Realize that. So this equation goes with B, this equation goes with C. The Monod equation, the growth rate is again related to external nutrient concentration, and the half saturation is the concentration at which growth is at half of the maximum growth rate.
What's S mean in these equations?
S is the external nutrient concentration, or substrate. It's from enzyme kinetics, and the S just means whatever substrate is being acted upon. This could be nitrate, ammonium, phosphate, silicon, anything that have a little A going to it in your diagrams. So there's different things that alter the uptake rate, because uptake rate's not happening by itself. So you can think of, for example, here is a trade-offs in nitrate uptake rate as a function of light, and ammonium uptake is a function of light, and then as a function of each other. So which takes more energy to use, nitrate or ammonium?
Nitrate.
Nitrate, right? So do you expect in phytoplankton nitrate or ammonium uptake to be more dependent upon light? So if it takes more energy, right, and they're phytoplankton are primary producers, and there's more light, what's it gonna have a bigger effect on? One that requires more energy, right? So which required more energy? Nitrate uptake. And we can see that when we have light here against the nitrate concentration, uptake rate, you have a bigger effect, whereas if they're in the dark, they take up almost no ammonium, but then they get up to saturation with almost no light at all. They've got enough energy. That's another way of looking at it. Okay, so metabolically, if ammonium and nitrate are both floating around in the environment, which do you want to take up first? Ammonium, right? And so we see that the nitrate uptake actually falls off with increased ammonium concentrations. So they just turn off their biochemical pathway to take up nitrate and just concentrate on the ammonium if the ammonium concentrations are high. So you can imagine that Vmax could be a function of light, can be a function of other nutrients, it can be a function of temperature, a whole bunch of different factors in the environment. So that brings up the idea of what nutrient concentrations actually are in the environment. You know, why would it matter? If they're always super low, then everybody's competing for nutrients. If they're always super high, then it doesn't matter what the relationship is between nutrients and uptake. And this is just the idea of the reference and current medium concentrations for nitrogen and total phosphorus across what they call nutrient ecoregions. And these are just major chunks of the US that might be expected to vary in nutrients for natural reasons or because of high degrees of human impact. And what we see is that essentially these turn out to be fairly low nutrient concentrations that are ambient, but that the current nutrient concentrations in many of these ecoregions, and particularly the Corn Belt here, that's Iowa in that area, lots of nutrient concentration. And then there's some stimulation of phosphorus by phosphorus as well. So putting it into context of what we know about nutrient uptake, at least all we can say is that from this graph is that there's a lot more nutrient out there than there used to be. You know, on average, the average now is higher than it turns out the average is higher in most cases than the upper 95th percentile in most of this water. So there's a lot of nutrient coming into the waters. So that brings up the question, does it matter? relative availability of nutrients, what is nutrient limitation, is there any more limitation anymore? And then how this might alter the community effect. And this is a basic ecological concept related to competition for use of nutrients. To review is the relative availability of nutrients in the world's rivers compared to what makes up the typical primary producer. So if you take a bunch of plants and algae and grind them up and analyze all the compounds that are in them, these are the ratios they occur at. If you take a bunch of river water from all over the world, mostly not impacted by humans, this is the ratios that everything occurs at. Molecules, atoms relative to molybdenum. If you take the ratio of those two, you can see where the demand is much greater for some than the supply is. And nitrogen and phosphorus truly pop out there. So that sets us up for the concept of nutrient limitation. And I want to talk about two things: Liebig's law of the minimum in the case for multiple nutrient limitation. So Liebig's law of the minimum is based on an idea that was created by agricultural fields by Liebig. And he suggested that if there's any process, the rate limiting step is the slowest step. So you can think about that as like if you're driving across Manhattan and you know that the stoplight at the intersection of College and Bluemont is always, or College and Anderson, is always, takes 10 minutes, but all the rest are 30-second stoplights. What's going to determine how fast you get across town is how long it takes for that to change. All right. Another way of looking at it is let's say you have an automobile plant and you're making cars and you have a 6-cylinder vehicle, and so you're getting you're getting 60 cylinders per day, so you could make 10 cars, but you're only getting 40 wheel brake and you're getting 40 wheel brake assemblies, right? So you can still make 10 cars a day, but if you're only getting 9 chassis assemblies, then you can only make 9. So the rate is what determines what goes in. And the argument then that Liebig made and has been extended is that only one nutrient can limit primary production. And that's something that idea has sort of taken hold in the ecological literature, and it's not necessarily true. And the reason for this is that when we actually physically go and measure the rate of nutrient limitation, that first graph that I showed you with Eric Strauss hunched over a series of carboys, we saw in Milford Lake that we added nitrogen, we got a little stimulus, but we added phosphorus and nitrogen together and we got a big stimulus. And this is a fairly common response in looking at the literature. And so we have a variety of different sources here, probably 10 to 50 sources depending upon which it is. And we see that in lakes, when you do these experiments, maybe 18% of the time you get no response. And you get a nitrogen response, say another 10% of the time. And a phosphorus response, we get maybe about 25–30% of the time. But almost half the time you need nitrogen and phosphorus together to stimulate primary production. Wetlands, commonly you get a nitrogen response, and about as commonly you get a phosphorus response. Then you can get N and P together, and sometimes you get a potassium or a nitrogen and potassium response together, being the dominant response. In streams, more commonly you get no response than in lakes, not as commonly as wetlands. You get a nitrogen response, 10%, 15% phosphorus, and again, almost half the time you need both nitrogen and phosphorus to stimulate primary production. So this has led to a situation where people have it's a little bit of a conundrum because organisms can fix nitrogen. And so why should they ever become limited by nitrogen? So what is it about nitrogen fixation that may make that not as attractive of a source of nitrogen for organisms? Requires a lot of energy, right? And then what's another thing about the way it's distributed phylogenetically? Who can do it? Somebody speak up.
Bacteria.
Yeah, bacteria, cyanobacteria and other bacteria. So if you're eukaryotic algae, you're out of luck, right? You're not gonna be able to fix nitrogen.